A determinant of a 2 by 2 matrix, A, and they give you A, B, C, D just as the matrix. First of all, pay attention to the notation. This means matrix when it looks like absolute value of that capital letter. They're talking about the determinant. It can also be noted like this, abbreviated determinant with an A. In fact, when you use your calculator, which we'll do later on, that's what it looks like in your calculator. This is the determinant. You multiply your diagonals and subtract. Always subtract. So you multiply A and D first and subtract the product of C, B. So you're just multiplying your diagonals and subtracting for a 2 by 2. All right? So very, very simple. Multiply 6 and 8. And subtract 5 times negative 2. Pay attention to your positives and negatives. It is always subtraction between them. However, if you're subtracting a negative, right, it's going to add. So in this case, you end up with 48 plus 10. Your determinant here is 58. We will use determinants for inverses and such. All right, that is your determinant. All right, 3 by 3. There's actually 2 ways to do a 3 by 3. Whichever method is okay. It doesn't really matter to me. I actually prefer the other method, but this is the first method they show. You can take a 3 by 3 and you can basically shift these 2 rows and copy them over here. Instead of having one diagonal from left to right and one diagonal from right to left, you have multiple, right? You have 3. And so you can just rewrite it, add your first 2 columns here, and then you do a product plus a product plus a product minus product, product, product. I will say, pay attention to this right here and the fact that they group it. It is imperative that you group it because order of operations will mess you up if you don't group these additions, okay? And so you can multiply your diagonals minus the product of your other diagonals, the sum of your products there. So this is one method. 3 diagonals minus 3 diagonals. That's a 3 by 3. And so we're going to do one that way, just so you can see it. So if I were doing this, I would copy these first 2 rows and I would slide them over here to create something like that, right? And then I would do product of the first set of diagonals. So I would say 2 times 5 times 1 plus negative 3 times negative 1 times 4 plus 4 times 0 times 6. All right, and that is one group, right? You have to group them. And then you're going to always subtract here. And then you're going to do bottom left to top right. So we're going to say 4, 5, and 4. Plus 6, negative 1, and 2. Plus 1, 0, negative 3. Right, and then you just do your operations there, right? So 2, 5, and 1. 3 and 4, that ends up being positive because of those 2 negatives. And then, of course, we have a 0. And then we have 4, 5, and 4. 6, negative 1, and 2. And then another 0. Right? So this is just basic. At this point, you're just doing order of operations, right? So we have 22 minus 68 equals negative 46. That would be our determinant using diagonals. Okay? Questions on that method? The minor of an entry. Remember, the entry is the element, and then they tell you where it's located with those little 2 numbers beside it. In a square matrix, is notated with a capital letter, M for minor, with the same row and column setting. And it's the determinant of the matrix formed by removing the row and column that that particular element is in. The cofactor of the entry is when you negate it. So first of all, let's talk about the matrix itself and what all of that is saying. So if I wanted to do the minor of, let's say, this 2, okay? The minor of the 2 is going to be the 2 by 2 determinant of what's left over if I were to take out the row and column that that guy's in. So if I were to take out this row and this column, that's where my 2 is, right? Then I would find the determinant of this 2 by 2 right here. That's the minor, okay? Cofactor is when you multiply by really what's in that 2. So if I'm going to take that 2 by 2, then I multiply it by that 2. They give us some examples here. They said, let's find the cofactor of C11. All right. You'll notice that we have this positive 1, this negative 1, and this positive 1. Well, where are they getting those? They're getting it from this pattern right here. Okay, this pattern right here. They call them even and odd positions. You start in the top left corner, and really it's goes alternating. So you see it's positive, negative, positive, negative. It would keep going. I mean, however big your matrix is, that would keep going. And then you'll see it goes positive, negative down as well. So your top left corner is always positive. It creates a diagonal of positives, and it keeps going like this, positive and negative diagonals, right? And so, for example, when they did this one, to get this minor here, they did the 2 by 2 matrix, so the same one that I was talking about up here, this 2. They said they wanted the minor of the 1, 1 position. So I go to row 1, column 1 position, that's that 2. And they want the minor. Well, the minor is the 2 by 2 that's left over, okay? So here's the position. Right here, they tell me the position, 1, 1. I find that position, that's right there. And I really ignore the row and the column of that position. And I take this 2 by 2 that's left over and do that determinant. 5 times 1 minus 6 times negative 1. The minor of the position 1, 1 is 11. All right? If I look here, the minor of the position 1, 2. Row 1, column 2, that's that negative 3. You'll see they just ignored the row and the column that that negative 3 is located in. And then they took the 2 by 2 determinants. 0 times 1 minus 4 times negative 1. There we go. The minor of that guy is 4. All right. 1, 3 over here. Same thing. They did the minor. Okay. Then they determined if it was positive or negative. That's what that cofactor means. Now determine what position that guy was in. Was he in a positive or an even, or was he in a negative position, odd? Okay? And so for this guy right here that lines up with this is a positive position. This would be positive, 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 negative, negative, positive, right? And so it just creates these diagonals of positives, negatives. So when they did the cofactor here, they just multiplied by positive 1. It didn't change. But this right here is in a negative position. So they multiplied this one by negative. This one is in a positive position, so they didn't change that one, okay? And so that's going to help us do determinants of 3 by 3s a secondary way, using your cofactors, okay? So let's look at using your cofactor to do a determinant. They have all these words. Determinant of an n by n matrix is the sum of the product of the entries in any row or column and their respective cofactors. For example, expanding the ith row, and they give this to you. What does all that mean? Well, you choose a row or a column. It doesn't matter which one. I always choose the easiest. If there's a 0 in the column, I'm probably going to choose that guy, right? Because he's going to 0 out. And you use that column and every single number in the column to multiply that by its cofactor, and then add those up. That's what we're doing, okay? So like if I were doing this, my personal preference here would be this one right here, column 1. Why? Well, because one of my guys is going to 0 out. Okay? They want us to do it two ways. So we're going to do it two ways so you can see both ways that we do it. The first way they want us to do is using row 1. That's this guy right here. All right, so row 1, we're going to use that to find our determinant. And so I'm going to choose the 2 first. So I'm going to start with a 2. So I'm going to say 2. It's in a positive position, so this isn't going to change. It's going to be a 2. And I will multiply it by the 2 by 2 determinants that is left when I ignore the row and the column that 2 is in. The 2 by 2 that's left is 5, -1, 6, 1. So I have 5, -1, 6, 1. That's my first one. All right? I'm going to add to it the 3 position. That 3 position is in an odd position, right? So I'm going to change that sign. It's going to be a -3 times a -1 before I do that determinant. I have to change the sign. And then I'm going to do the determinant of whatever's left when I ignore this row and this column. All right, that's 0, -1, 4, 1. Right? And then I'm going to do the last one, which is the 4. It's in an even position, so it's positive. I'll leave that guy alone. And I'm going to do the 2 by 2 that's left here, which is the 0, 5, 4, 6. All right, that's the other method, right? So it's not hard. We're just going to say, well, this is going to give me a 2 times the 5 minus a -6, right? This is going to give me a 3 times the 0 minus a -4. This is going to give me a 4 times the 0 minus 20, the 2 by 2. And so then I'm just going to add it up. So I have 22 plus 12 minus 80 equals -46. That's that guy. So why would I have chosen the first column, B, here? Well, because I have one less guy to do, right? When your outside guy is a 0, 1, you don't have to worry about its positive or negative. 2, you don't have to worry about what the determinant is. It's going to be times 0, right? And so if I were to do this column instead of the first row, I would only have to do it twice. So this first one's going to be exactly the same. It's going to be 2 times that 5, -1, 6, 1. The second one's going to be 0 times something. I don't even write it out. I don't have to worry about it. And the third one is going to be 4, but it's times a different determinant. It's times this guy right here. So -3, 4, 5, -1. And so then I'm going to do exactly the same thing. This is going to be the 2 times the 11. This is going to be 0, right? And then this guy is going to be 4 times the 3 minus the 20, right? Which should also give me 46. All right, questions on doing it that way? All right, try one. So there will be times when I give you 2 by 2s and 3 by 3s that I say, use this method or this method to solve. And so I must see that you've used either the diagonal method or the cofactor method, right? I must see that work. But you're welcome to check it. It's a nice check mechanism. If I ever give you one larger like this, I'm not going to require you to show me a method because it's going to take you all day to do that, right? So on your calculator, you have this matrix button. You have to get to it by using this second and matrix. When you do that, you actually pull up a screen that'll have A, B, C, D, E all the way down, right? And so if you go into it, you will see that you have 1 with an A, 2 with a B. If you have a TI, you should see that concept, right? And so if you are on it, you can go over to the edit. So you can go all the way over to edit, hit enter, and then it gives you the option to tell the dimensions of that matrix. So by the way, if you have other matrices loaded, you have to, on the edit screen, go down to a new one that is blank, okay? And you'll see the dimensions. It defaults at 1 by 1. You can put in 4 by 4. And it'll create this 4 by 4 matrix, right? And then you go through and you add all of your elements to your matrix, right? It goes across. So it goes by rows. So as you enter this, you can hit 1, enter, 2, enter, 0, enter, -1, enter, and it drops you into the next row, okay? So it'll let you enter all the way across until you have filled in the matrix all the way across, right? And then you'll notice that if you go back to your matrix screen, you have a 4 by 4 matrix in that position that you just loaded, okay? And so that's how you load the matrix. That's how you load it. And then on your matrix screen, once you've loaded it, you can go to math and you can do the functions. So once you've loaded your matrix, you should be on your home screen here. So now you're going to go into your matrix menu. So second, usually x to the -1 on most TIs. Go over to math in that menu and then choose option 1, determinant. And on your main screen, you should see the notation for determinant that looks like this. It should have opened a parentheses. All right. Now you're going to go into your matrix menu again, second matrix, and you're going to choose the matrix you just loaded. Whatever matrix. If it was A, go down to A and hit enter. It will have thrown it into brackets like this, right? Close your parentheses and hit enter. So this equals 6. All right, Kramer's rule. They give actually the whole proof. I'm not going to go through it just because I feel like, yes, sometimes it's really good to know where it came from. Sometimes it's going to confuse you. So in this case, I think it's going to be more confusing because they use a lot of long and gruesome substitution to show you the proof, right? And so it's easier just to know that it works. But if you want to know how it works, I'll be happy to show you. So Kramer's rule basically says that if you have a systems of equations, you can take the coefficients of all of your variables, whether it's a 2 by 2 xy or whether it's a 3 by 3 xyz, and you can find that determinant, the determinant of your coefficients. And that's kind of your base that you're going to start from. And then you find a determinant for all of your x's, if you were to fill all of those in with the answer, a determinant for your y variable, and a determinant for your z variable, or however many variables you have. And if you take the determinant of each individual variable and divide it by the determinant of the coefficients, that is your x, your y, and your z of your equation, right? And so they actually start off with a 3 one, which I kind of wish they wouldn't, but they start off with a 3-term one, so that's what we're going to do. And we're going to show the process, and you'll probably remember it as we do it. So let's look at this first example. Use Kramer's rule to solve this systems of equation. So the first thing you want to do is you want to set up your coefficients in a matrix. So we're going to label it A, X, A, Y, A, Z so that you can see the difference. So this is just my coefficients. Remember, if you don't have one, put a 0 in. So 1x, 0y, 3z, 3x, -2y, 0z, and 0x, 2y, and -1z. All right, so that is my matrix of my coefficients. So if I want to find my determinant, you can do it either way that you desire. You can either do it by the diagonals, or you can do it by your row column method. I'm probably going to do it by my row column method just because I have, I'm going to do this first row and I'm going to find my determinant. So I'm going to say 1 times -2 times -1, which is 2 minus 0, right? And then this guy zeroes out, so we don't have to worry about him. And then plus 3 times my 6, again, minus my 0. So my determinant here is going to be, what, 2 plus 6, hopefully. So this, it ends up being 20 either way. I just couldn't figure out which one they did. It doesn't matter. They did the third row. Either way, you're going to get 20. This is just your base. So we're going to set this guy aside, and now we're going to use our X, Y, and Z. All right? So we're going to do an AX. This represents my X column, right? These are all of my X coefficients. Those are my X coefficients. That's the column that I am going to replace, and I'm going to replace it with my answers. So I'm going to say 2, 6, 8, 0, negative 2, 2, 3, 0, negative 1. So I only change this first column, my X column. And I'm going to go through the whole process, and I'm not going to do it out on here, of finding my determinant for this guy. In this case, this determinant is 88. All right, 88. I'm going to do the same thing with my Y column. I'm going to leave the first column alone. I'm going to replace the second column, which is my Y. I'm going to leave the third column alone. And I'm going to find my Y determinant. And then I'm going to do the same thing with my Z. All right. And so I'm going to leave the first and second column alone. And I'm going to replace the third column. And then I'm going to do it again and find that guy, which is negative 16. All right. So I have all these. To find my X value, my X is going to equal this 88 divided by the 20. My Y is going to equal this 72 divided by the 20. And my Z is going to equal this negative 16 divided by the 20. If I wanted fractions, I would just reduce. They did it in decimals, which is nice. So technically my point are in decimals, 4.4, 3.6, negative 0.8. All they did was put it in decimal form. Okay? So this is Kramer's rule. I will say it's much faster to do it with a 2x2 than a 3x3. I will also say that me personally, I would probably use Kramer's rule for one variable, right? And then I would take that variable and I would like plug my X in here and solve for my Y. And then, solve for my Z, and then I'd plug my Z in here and solve for my Y. I would not do 3 of these. Does that make sense? So I'm always going to do the path of least resistance when I do something like this. If I have a 2 variable somewhere in there, I'm going to solve for one of those with my matrix. Then I'm going to plug it back into my equations and solve for my other variable. I'm not going to do a 3x3 4 times. Right? That's not what I'm going to do. That's not logical. Okay, so if you have to solve by Kramer's rule, it does not mean that I'm telling you have to solve the entire thing by Kramer's rule. But you do need to solve a variable, and then what's your best method to go from there. I just want to show you, first of all, 2x2s are way easier. But there's 2 scenarios that can happen when your coefficient is a 0. It does not always mean we have a problem. Now, when we get to inverses, which is next section, a 0 you have a problem. It won't have an inverse if your determinant is 0 because you're dividing. But in this case, it actually can mean one of 2 scenarios. So you'll see that both of these have a 0 for my coefficient matrix, okay? You cannot stop there. You have to then go and say what's actually going on with it. If these are numbers, then yes, you have a number divided by 0. This is undefined, and you're going to say there is no solution, all right? So if your coefficient is a 0 and your x's and y's are not, then you have an undefined, all right? However, if this is a 0 and your x's and y's are also zeros, this is actually the entire system that is true. If I were to get this in simplest form, I would say that the equations represent the same line, all right? So if I were solving this by my other methods that I've done, I would get a true statement if I did this. I would get something like 0 equals 0, right? True statement. If I were solving this from other method, I would get something like 3 equals 0. False statement, okay? So you can't stop at the coefficient matrix when you're solving these if you get a 0. You have to at least go on and see if one of those variables is a number, okay? And then all of a sudden you can say, okay, undefined, or if there's zeros, you can say, yeah, it's actually the entire system, okay? So I just wanted to show you these. We don't necessarily need to work them out, but I wanted you to see what it looks like. All right, try it. And I gave you a 2x2. All right, so you can find area of this, well, technically it's two triangles. You can find an area of a triangle using matrices. So basically you have, of course, a triangle is going to have three vertices, 1, 2, 3, right? X, Y, X, Y, X, Y, right? And you can use this setup, your X's, your Y's, and then all ones right here. Get the determinant of this guy, the 1/2. Your triangles usually have 1/2, base times height, really, something like that. Positive or negative. So when you're doing this, the reason it's positive or negative is you're finding an area and your determinant ends up being negative, you're going to negate it, right? Because you're finding the area. And so you can think of this even as direction. I think I give you a direction one at some point where they went this far this way, this far this way. And so those are technically coordinates when they tell you direction as well. And this will be another way to find the area of a triangle. Granted, a triangle on a coordinate plane type setting, but an area of a triangle. Now, why did they give us this example? Well, this is just two triangles, right? That's all this is. So if I were to cut this down from one vertex to the other, then I should get a triangle, right? And so I don't know which way they cut it, but we'll see. So if we cut this across, I have two triangles, right? And so I can do a matrix this way. I can set up the first one. We'll just do the top guy. All right. So my first one, all my X's. Again, it doesn't matter which order you put it in. 0, 1, and 6 are my X's. And then 3, 7, and 2 are my Y's. And you'll notice these do have to pair up, right, with these coordinates. And then this third guy is all 1, 1, 1. That's what I'm going to do. All right. And then I am going to do my determinant. So I'm just going to find the determinant for this guy. And I have two triangles, so I do have to consider the positive and negative in 1/2 there when I do this determinant. It ends up being positive or negative 15 minus 40. So positive or negative 1/2. And I end up with, and they used the first one so that they zeroed one out. But you end up with 15 minus 40. I'm not going to do all the ins and outs of it. 15 minus 40 is going to be negative, so I'm going to multiply by negative 1/2 so that my area is positive. So 25 over 2. And then that's this person. So I need to do this guy right here. Do the same thing down there for that one. And we're going to do those coordinates. So I have 0, 3. I have 4, 0. And I have 6, 2 for that one. And I'm going to do the same thing there. Positive or negative 1/2 times those determinants. And I think they used the middle one. But you end up with 6 plus 8, which is positive. So we're going to multiply that by positive 1/2, which gives us 7. All right. So we have two triangles. If I want the area of the entire thing, what do I need to do to those two triangles? I just add them. Composite figures, right? We learned it in geometry. You do need a common denominator, so it's 14 over 2. But I think they put it in decimals anyway. So we have 12.5 plus 7. We get 19.5. They didn't give us units, so you'll see them do something like that, which indicates it's an area. It's a square, right?